So number 4, let's start with that one. It says use derivatives to find the critical points and the inflection points. You can see in number 4, f of x is a cubic. F of x equals x cubed minus 9x squared plus 24x plus 5. Find, again, the critical points and inflection points. Critical points are where the derivative equals 0, and sometimes also where the derivative is undefined, even when the function itself does exist, is continuous. Inflection points are where the second derivative, well, not only is 0, but actually changes sign as well. The concavity of the graph changes either from concave up to concave down, or the other way around, from concave down to concave up at an inflection point. So you take derivatives. The first derivative is 3x squared minus 18x plus 24 for this problem. Define critical points, set that equal to 0, and solve for x. So I write set equal to 0 to emphasize this function is not always 0, but I'm looking for the values of x where it is 0. It's quadratic. You could use the quadratic formula. Maybe we're lucky and we can factor it. Actually, you can make it a little simpler looking, and this is probably a good idea by dividing everything by that common factor of 3. If I divide everything by 3, I get x squared minus 6x plus 8 equals 0. That's not the derivative. It's the derivative divided by 3, but it's 0 at the same spots where the derivative is 0. And in this case, we are lucky. We can factor it as x minus 4 times x minus 2. In general, you'd have to use the quadratic formula. In general, you could get irrational critical points. That's possible, involving square roots of non-perfect squares, like square root of 5 or something. You also even could get imaginary complex number roots. That's not happening here, but it could happen in general. If your cubic function doesn't have a maximum or minimum, if it just goes up like that, there won't be any critical points. There won't be any real roots to its derivative. That can happen sometimes. But in this case, the critical points are 1 and 4. Critical points, or 2 and 4, excuse me, are 2 and 4, where the derivative equals 0. It doesn't ask you in this problem to classify the critical points. But let's do that. Let's go beyond what's being asked for. Now, if you know what the graphs of cubics behave like, especially when the coefficient of x cubed is positive, like it is here, when you've got critical points where the derivative is 0, the graph has to look like this. Go up, then down, then back up again. So without applying the first or second derivative test, I know there's going to be a local maximum at 2 and a local minimum at 4. A high point, like the top of a little hill, at x equals 2, and a low point, like a valley, at x equals 4. But let's confirm that with the first and second derivative tests. With the first derivative test, you make a number line. And on that number line, you mark off the places where the derivative is 0. In this case, 2 and 4. And you test the sign, plus or minus, of the first derivative on each of the intervals the number line has been broken up into. Numbers less than 2, numbers between 2 and 4, and numbers bigger than 4. Do you literally have to find f prime of such numbers? No, you can just think about it. But you should show your work like I'm doing. I'll go ahead and imagine plugging a number like, well, how about -1 in for x into the derivative here. Again, you could calculate its value, but you can just think about its sign. Okay, this is not the derivative here, but it's the derivative divided by 3. It's going to have the same sign. X minus 4 times x minus 2. When you plug in x equals -1, in both spots you get 2 negative numbers. The product of 2 negative numbers is positive. The derivative is positive. So f itself is increasing on this interval, which we already knew. We're just confirming what we already know. If you plug in a number between 2 and 4 into the derivative, like f prime of 3, again, this is not the derivative right here, but it is the derivative divided by 3. It's going to have the same sign. You plug in x equals 3, that'll be negative, that'll be positive. The product of a negative and a positive is negative. So f itself is decreasing. And you plug in a number over here like 5. You get the product of two positive numbers. This is positive, so f itself is increasing. In making this picture, I'm implicitly using a theorem that I haven't actually officially written down in class yet. It's called the increasing function theorem. I've mentioned it before. If the derivative is positive on some interval, which this is implicitly showing, also because it's a nice continuous function, f prime is really positive for all x less than 2. The increasing function theorem implies that f is increasing on that interval. It's going up, like you see in this picture. Makes intuitive sense? It is a theorem. You can prove it with the mean value theorem. It almost sounds too easy, right? The derivative is positive, the slope's got to be positive, the function's got to be going up. What could be simpler? Well, I will warn you, probably mention this, talk about an example of this on Wednesday. There are examples of really weird functions where the derivative is positive at one point, but the function is not increasing near that point. Doesn't that sound weird? The derivative is positive at some point, but the function is not increasing near that point. Emphasis on the word point, one number. That doesn't contradict the increasing value theorem, because the increasing value theorem says the derivatives, if the derivative is positive for all x in some interval, not just a one point, then the function is increasing on that interval. Again, I'll go into depth on Wednesday as part of our review for the exam, that if it's just at one point, that's not good enough. Might seem like it's good enough, but it's not. Likewise, there's a decreasing function theorem that says if the derivative is negative on some interval, then the function's decreasing on that interval. Again, 1 point's not enough. It's got to be an entire interval of numbers. And if it's positive over here, it's increasing. This up, down, up stuff with the derivative is also related to the first derivative test. What we've done here is confirm the derivative changes sign from positive to negative at 2 and from negative to positive at 4. Intuitively, that's why the graph's got to look like this, and that's why there's got to be a local maximum at 2 and a local minimum at 4. Now, I drew an axis there to show you where 2 and 4 are, but that doesn't mean the graph looks exactly like this with respect to the horizontal axis. It could be higher or lower. I'm just showing you the x locations. You could also confirm that you have a local maximum at 2 and a local minimum at 4 with something called the second derivative test. What does that say? I did mention these last week. Find the second derivative, f double prime of x. I've got to differentiate this before I divide it by 3, right? You see where I'm pointing? The derivative of that is going to be 6x minus 18. Do that in your head. 6x minus 18 is the second derivative of the original function. If you plug in the critical points into the second derivative, 2 and 4, and test the sign of the second derivative, it also confirms there's a local maximum at 2 and a local minimum at 4. Why? The second derivative at 2, if you plug in 2 in here, you get 12 minus 18, negative 6. It's a negative number. If you plug in 4, you get 24 minus 18. That's a positive number. The second derivative is also a nice function, continuous. What this is confirming is that the second derivative of the original function is negative near 2 and positive near 4. The original function's concave down near 2 and concave up near 4. That's another reason why there's a local max at 2 and a local min at 4. The top of a little hill at 2 and on the bottom of a little valley at 4. Do you have to use both tests? No, you don't. One test or the other is good enough. It's good to see they both work, and you should be able to use either test. Maybe in the directions on an exam problem, I'll say, use the first derivative test, or maybe I'll say, use the second derivative test. So you should be able to use both. But to verify, well, we verified you don't have to use both. One of them is good enough. Again, we're not being asked for what the local maxes and mins are, but I wanted to do that because that is still part of this section. You're only asked to find the critical points and the inflection points. What are the inflection points? Where that's where it changes concavity. That's where the second derivative changes sign. The second derivative is a nice simple function, 6x minus 18, which you can also write as 6 times in parentheses x minus 3. That's 0 when x is 3, and it changes sign. Right? If x is less than 3, like 2, you get a negative second derivative. If it's bigger than 3, like 4, you get a positive second derivative. The second derivative is changing sign at x equals 3. There's an inflection point at x equals 3. Inflection point at x equals 3. The graph changes its concavity at 3. It's concave down to the left of 3 and concave up to the right of 3. What's this good for? Numerous things. One thing it's good for is it does help you, if you are careful, to take this information and draw a good graph of the original function. Again, this is its shape. I haven't verified how high or low it should be. Plotting points would help you do that, even if you didn't have technology. More importantly, especially after the next exam here, we're going to get into real-life applications of this stuff. Word problems, yes, sorry, word problems, but they are related to real-life applications where, well, I mean, yes, technology can still help, but it's good to be able to confirm this without technology. For one thing, because oftentimes in real-life applications, you have unknown parameters in the function, some unspecified constant a. And if you don't know what a is, how can you graph it? If you're not told what the constant is. But doing this kind of analysis is still helpful. And it's also really helpful for multivariable calculus, even beyond what I've shown you, where you can't even visualize things at all. So you have to rely on the calculus calculations, the symbolic calculations where you do derivatives and second derivatives and you figure out where things are 0. You have to rely on them because maybe it's a problem with 10 variables. You can't visualize it because it's in 10-dimensional space, right? No human can imagine such a thing. I'm serious when I say those kinds of things. That's what goes on in real life advanced applications of multivariable calculus. So you have to trust the math. In calculus 1, we can actually draw pictures that help you believe it. But it's good to get practice with the symbolic manipulations to help you understand and be able to do multivariable calculus kinds of things. And yes, let's go ahead and write down, confirm. We say there's a local max at x equals 2 and a local min at x equals 4. By the way, the word local is also sometimes called relative max and relative min. I prefer the word local because it's nearby the point. What do I mean by that? That's a high point on the graph, but not the entire graph, right? The graph goes higher over here. It's a high point of a small little hill. Local. not global. This is a low point of a valley right here. But it's not the lowest point in the graphic, it's lower over here. Local, not global. These tests are for local extreme points, not global extreme points. If you're asked for the local max and local min values, emphasis on the word values, that means function outputs, not inputs. So the local max value with an emphasis on the word value is f of 2, the original function of 2, not the derivative, not the second derivative. And to find that, you have to go back to the original function and plug it in. I've got it on the screen here. Down here, x cubed minus 9x squared plus 24x plus 5. Plug in x equals 2. Do that with me in your head here. 2 cubed is 8. 2 squared is 4 times 9 is 36. 8 minus 36 is negative 28. But then 24 times 2 is 48. Negative 28 plus 48 is 20. Plus 5 is 25. It looks like the local max value, if I didn't make a mistake there, is 25. Is that right? Okay. And the local min value, oh, now I got to do a harder calculation in my head. Local min value, supposed to be min here, is f of 4. 4 cubes, 64. 4 squared, 16. 16 times 9 is 144. 64 minus 144, negative 80. Is that right? 64 minus 144. Negative 80. Plus 96. 16 plus 5 is 21. Okay. Local min value. So that could help you graph it more accurately. The second coordinate to this point is 25. The second coordinate to that point is 21. I really should draw the graph higher if this is the x-axis here. Let's confirm it with the calculator. Plug in the original function, x cubed minus 9x squared plus 24x plus 5. Probably you want your window to for sure contain 2 and 4. Maybe say 0 to 6 is good enough. For the y min, I don't know, maybe I'll go ahead and keep it at -1, but I want to go up to at least 25 here for the y max. Maybe I'll go up to, well, maybe I'll make this -5 and make this 35 and make these tick marks 5 units apart or something like that. Let's see how it looks on this window. You graph it now. You do see the y-intercept there is 5, as it should be. If you imagine finding f of 0, you get 5. See the graph goes up, then down, then back up again. The second coordinate of this point is 25. Let's see if that seems right here. 5, 10, 15, 20, 25. Yep. Second coordinate of that point is 21. Yes, a little bit above 20. These tick marks over here are 5 units apart. Okay. Any questions at all? Is the inflection point just the x coordinate? Well, you could compute the y coordinate too. Actually, it would be halfway between these two. It would be 23. 3 f of 3. If you compute f of 3, you should get 23. Here I'm thinking of it as just the x coordinate. You could call it the entire point as well on the graph. All right, let's do another example. Oh, how about number 7? That doesn't look so easy. There's a natural log in there. f of x equals 5x minus 3 times natural log of x. F of x equals 5x minus 3 times natural log of x. It's number 7. The directions are the same. Find the critical points and inflection points, but I'll do more. I'll find local maxes and mins, confirm it with the first and second derivative tests, and sketch the graph of the function. Procedure is the same. Find the derivatives. F prime of x. Derivative of 5x is 5. Derivative of minus 3 ln of x is minus 3 over x. Set that equal to 0 to solve for any critical points. You can add 3x to both sides and write it like this. You could then cross multiply. Multiply both sides by x and divide both sides by 5 effectively. And you'd get x equals 3/5. That's your critical point. Is there a local max or a local min at 3/5? Make a number line. The domain of this function is when x is positive. I will draw 0 on the number line just for reference, but it's not a critical point. This happened last week with an example. I made 0 on this line just for reference as the edge of the domain of the function. It's not a critical point, though, because the function is not even defined there. Plug in the number between 0 and 3/5, like, I don't know. How about 1/2 into the derivative? Imagine plugging 1/2 in there. Right there. 3 over 1/2 is 6. 5 minus 6 is -1. F prime is negative. So F itself is decreasing. Plug in the number over here like 1. You'd get 5 minus 3, 2, positive. So F is increasing over here. Again, I am using the fact that F is a nice function. When x is positive, that's a nice continuous function. So I only need to test these individual points. If I know the derivatives at 1/2 is negative, I know the derivative is negative in the entire interval here. If I know the derivative at 1 is positive, I know the derivative is always positive over here. The function is continuous when x is positive. So it's decreasing, then increasing. The first derivative test would tell me then that at 3/5 I have a local minimum because the function's graph's got to go down and back up again. Very intuitive facts, the first derivative test, the second derivative test. Proving them is hard, though. We don't prove them in this class. There is a math major class called real analysis where they prove those things from scratch. Okay? It takes a while. From the start of the class, it takes like 2 months to get there. Yikes. Or cool, yeah. What do they have to do all in the meantime? They have to even define what a real number is. That's part of what they have to do. What is a real number? You ever think about that? Like, what is square root of 2 even? You say, well, my calculator tells me, doesn't it? Doesn't my calculator tell me square root of 2 is that? Well, kinda, but that's not really square root of 2. Square root of 2 is irrational. The decimal expansion goes on forever and ever without a repeating pattern. Mathematica could show us, say, how about 10,000 digits? There they are. 10,000 digits of square root of 2. You want to memorize it? Go ahead. I'm not going to. But wait a minute. If it goes on forever and ever, who's ever going to square such a number and show that you get 2? How's this even possible? Do you ever think about that? How do we know if the decimal expansion goes on forever without a repeating pattern? How do we know there is a number whose square is exactly 2? It's a deep question. really hard to answer. And actually, in real analysis, they answer it, but they do it in kind of a funny way. They make some assumptions that help them answer it. So you could question those assumptions. Anyway, it's an issue. We don't worry about it in classes like this. Just say, okay, that's for the mathematicians to worry about. What about inflection points and the second derivative test? What is the second derivative? It's better to write the function as 5 minus 3x to the negative 1 if I want to take the second derivative. Not that you have to, but better, because then you can avoid the quotient rule. I mean, I like the quotient rule, but I also like avoiding it when I can. F double prime of x, the derivative of 5 is 0. The derivative of negative 3x to the negative 1 is negative 3 times negative 1 x to the negative 2. This simplifies to positive 3x to the negative 2. And that's never a negative quantity when x is a real number. By definition, x to the negative 2 means 1 over x to the positive 2. This is always a positive quantity if x is a real number that's not 0. And it's certainly positive when x itself is positive, which is the domain of the original function. So technically speaking, even though this formula is defined even when x is negative, it's only the derivative of the original function when x is positive, because the original function is only defined when x is positive. Anyway, it's positive, including at 3/5, the critical point. Therefore, the graph's got to be concave up. Yet another confirmation that at this critical point, it's a local min. There is a local min at x equals 3/5. The local min value would be f of 3/5, f of 0.6. So there's a logarithm involved, so that's not so simple to figure out. Need technology. 5 times 0.6 minus 3 times natural log of 0.6. The local min value is approximately 4.53. I just plugged 0.6 into the original function. That's the lowest possible output, approximately. Are there any inflection points? Does the second derivative change sign? No, it doesn't. This doesn't change sign at all. It's never negative. Even if x itself were negative, it's not negative. It is undefined at x equals 0, but that doesn't mean it changes sign. There's no inflection points. The graph's fairly simple. Kind of parabola-like, though it's not technically a parabola. If I were to try to graph it without technology, I'd also remember that, hey, the natural log is undefined at 0. And in fact, the natural log of x has a vertical asymptote at 0. Goes down forever and ever as you approach 0 from the right. Now I'm subtracting 3 natural log of x, so probably that flips it across the axis. It goes up forever and ever as x approaches 0 from the right. And that makes sense based on what we've done so far. The graph's going to look something about like this. And it grows in the long run slower than 5x does because I'm subtracting the 3 natural log from that. It's not going to grow very rapidly. So it's not really a parabola. It's not symmetric about the low point here. There's 0.6, approximately 4.53. And you could use your calculator to confirm that. I won't take the time. Well, maybe I should take the time to just show you how to use the minimization feature in the calculator. That's probably worth showing you. So I will take the time to do it, I guess. Plug in the function 5x minus 3 times natural log of x. There's the function, pick a window. I'll go to 0 to maybe 3 instead of 6. I'll make my tick marks. How about I make them 0.6 apart? So that the first tick mark on the x-axis is where the low point is. That'll be nice. It goes down to 4.53, so maybe 0 to 15 or something. Or how about I make my first tick mark there, 4.5 at 4.53. So my low point will be at the first tick mark on the x-axis and first tick mark on the y-axis. Graph it. It looks pretty flat there. It looks like there could be a lot of low points. There's actually only one lowest point. Let's see how the calculator feature in the calc menu, which is above trace, does in computing that minimum. It is an option to compute the minimum. Pick a left bound, pick something less than 0.6 for x. I'll pick there. Then a right bound, pick something bigger than 0.6. Now you may not know where it is because maybe you haven't done the calculus. And it is approximating x to really close to 0.6, not exactly, and y close to 4.53. Why is it not getting x equals 0.6 exactly? Because it's using what's called a numerical algorithm, probably related to Newton's method, to tell you the truth, from the project. That's only giving us an approximation. It's a dumb machine. It just does what it's told, right? How scared should we be of AI? Well, I do think AI has some scary parts to it. I don't think it's got generalized intelligence. AI is programmed to do very specific things. Yes, it does learn, so to speak, but it can't do creative things as far as I know. Original thinking. It's doing what it's programmed to do. Now, that doesn't mean it's not dangerous. I read an article that somebody actually has programmed an AI to destroy the world. It was in a news article. It's like, what in the world are you doing? It could try to take over. That doesn't mean it's smart. It just means it's doing what it's programmed to do. Anyway, it's just a machine doing what it's programmed to do. You know from what we've just done here, the exact mins at x equals 3/5, exactly 0.6. Another example. Oh, maybe we should pick one that's a fraction, like number 12 there. F of x is x over x squared plus 1. This is actually something whose shape you should be able to draw without calculus. Let's do it. How? It's a rational function. Numerator and denominator are both polynomials. I see the numerator is 0 and x is 0. That's going to be the only x-intercept is at 0. I see the denominator is never 0 when x is a real number. So I'm never dividing by 0. I don't have any vertical asymptotes. I don't have any holes in the graph. It's defined everywhere. I see the degree of the bottom is bigger than the degree of the top, meaning the bottom grows faster than the top does as x gets big. So you got a big number divided by a really big number when x is big, meaning the fraction is close to 0. The x-axis is going to be a horizontal asymptote. It's also an odd function. It's going to have symmetry with respect to the origin. The graph's going to look like this. What we're after with calculus is exactly where the local max and local min are, though they will be symmetric about x equals 0, and exactly where the inflection points are here and here in the picture. Where are those exactly? Calculus can tell us. Now, I've got a quotient, so I could use the quotient rule. You actually can always avoid the quotient rule because you could also write this as x times x squared plus 1 to the negative 1 power. Then you would have to use the chain rule. It's not that much easier necessarily. The quotient rule is not that bad anyway. So low d high minus high d low over the square of what's below. On a gateway exam or on Friday's exam, when I just say find the derivative, it's good enough to leave it like that. But for the purposes of using the derivative, it's good to simplify. And if you expand this out and simplify, x times 2x is 2x squared. I'm subtracting it. You'll get 1 minus x squared on the top. If you set this equal to 0 to find the critical points of f, it's not as complicated as it looks. You can just focus on the top, because it's the only way a fraction is 0 is if the top, the numerator is 0. So this implies 1 minus x squared is 0, which you can factor, but you can also write like this as x squared equals 1. So x is plus or minus 1. Those are your critical points. Those are going to be these values right here. And I can already see from the picture there's going to be a local max at 1 and a local min at -1. The first derivative will change sign at -1 and 1. If you plug in a number less than -1, like -2, -2 squared is +4. 1 minus +4 is -3. Divided by a positive number, f prime is negative over here. It's also negative if you plugged in +2, because the derivative is an even function. The original function's odd, the derivative's even. Plug in a number between -1 and 1, like 0, into this, and you'll get a positive number. F is decreasing, then increasing, then decreasing again. Where are the inflection points? I got to find the second derivative and figure out where it changes sign. Go here, take the derivative of that with the quotient rule. Low. Oops, I forgot to square the bottom, didn't I? Sorry. That makes the derivative a little less pleasant here. Low d high minus high d low, the derivative of the low, I could use the chain rule for and get that. Yeah, this is looking not so pleasant. Over the square of what's below. Simplify. Sometimes you just got to do it. So I'm going to square x squared plus 1 and get this. Before I multiply by -2x, I will also multiply things here. I'll multiply the 2 and the 2x to get 4x. And then I'll multiply these two things, foiling in my head. Looks like if I didn't make a mistake, I'll get that. Yes, sometimes life is unpleasant. And you're just praying you didn't make a mistake. I'm praying right now I didn't make a mistake. Distribute the -2x through here. Get -2x to the 5th minus 4x cubed minus 2x. Distribute the -4x through here. Oh, actually the x squareds cancel there, so that's nice. -4x times 1 is -4x. -4x times -x to the 4th is plus 4x to the 5th. Okay, so this second derivative is not very pleasant. Combine the like terms, looks like we get 2x to the 5th. 6x to the 5th? No, okay, I got a negative sign there. Minus 4x cubed minus 2x if I have not made a mistake. Now I very well could have made a mistake. I do make plenty of mistakes. Yeah. Can factor out a 2x. Can that be factored anymore? Not very easily. I do see this is going to be 0 at x equals 0. That's one possible inflection point. Any others, it would have to be where this part's 0, which is actually not as hard to figure out as it looks, because even though it's a 4th degree that I'm pointing at right now, you could use the quadratic formula to solve it for x squared instead of x. That makes sense? Because x to the fourth is x squared squared. I didn't realize it was going to be this unpleasant. Did I make a mistake? Yeah, thank you. -6 there, and a -3 here. And that can be factored, actually, yeah. So that's better. But in general, you could use the quadratic formula. You could factor this as x squared -3 times x squared plus 1. All I'm doing effectively in writing that is treating the x squared like it's x to the fourth, like it's an x squared, and the x squared like it's an x. It's the same kind of method as usual with factoring.
Like the first line, I think x squared plus 1 can be canceled out from top and bottom.
Yeah, I could have done that at the beginning. You're right. Up here, I could have canceled this one of these x squared plus 1s and one of those with one of those. Yeah, that would have been simpler. There's nothing wrong with what I did. It's just not maybe as efficient as could be. So set this equal to 0, solve for x. It's going to be 0 when the top is 0, which occurs at 0 or plus or minus the square root of 3. That one right there is never 0. Hey, square root of 3 is about 1.7. It's looking reasonable. 1.7 there. And negative 1.7. Looking reasonable. Is it really right? Maybe we should use Mathematica to check this one. Let's just check that what we've done is right here on Mathematica. Here's the original function. If I can type. Its derivatives simplified are those. And yes, Mathematica did cancel one of the x squared plus 1s for the second derivative. And in fact, I could do that at the end here as well. I could cancel this with one of those. Looks like I got it right. And yeah, that second derivative is going to be 0 when x is 0 or when x is plus or minus square root of 3. If you're feeling uncertain, you could do this. Solve with a capital S. F double prime of x equals 0 with 2 equal signs. Yeah, 0 plus or minus square root of 3. Those are your possible inflection points. And in fact, they are actual inflection points. The graph really does change concavity at those points. Over here, it's concave down. The second derivative is negative. In here, it's concave up. The second derivative is positive. At 0, there's an inflection point. It changes to concave down and then concave up over here. You could argue, okay, again, in the past, before calculators and other kinds of computing technology came along, people had to use these techniques to help them draw accurate graphs. I did emphasize a half an hour ago that it's still important today, even with the technology, because it's important, including after exam 1, to be able to handle problems where you have unspecified constants. So you can't necessarily make enough graphs to understand what's going on, but you still want to analyze it. It's still worthwhile, even if we didn't do that, because it helps you understand why the graph looks the way it does. It can help you understand that. These functions are all related to each other. The original function, the derivative, and the second derivative. They're interacting with each other, so to speak, in ways that are helpful for sketching graphs and solving applied problems. See that a lot next week. This figure that you see is the graph of f prime, not f. On the graph, mark the x values that are critical points of f. At which critical points does f have local maxima, local minima, or neither? You're told this is the graph of f prime, not f. Mark the x values that are critical points of f. And where does it have local maximum, minimum, or neither? Critical points of f for nice situations are where the derivative equals 0. Again, for not so nice situations, it can also sometimes be where the derivative is undefined, even when the original function is defined. That does happen sometimes. Like with the absolute value function. Graph looks like a V. Continuous everywhere, but not differentiable at 0. The derivative is undefined at 0. But 0 is still a critical point. Because it's a place where the original function is defined, but the derivative is undefined. Make sense? Graph looks like a V, corner at the bottom there, not differentiable. It always looks like a V no matter how close you zoom in. That's technically a critical point as well. But this is a nice smooth graph, no corners. For the derivative, the original functions graph would be similar. Critical points of the original function, which is not drawn, are where the derivative is 0. The x values where the derivative is 0. There's 3 of them, right here, here, and here. If you had a scale on the horizontal axis and you could identify those numbers, then you could say what numbers those are. Which are local maxima, minima, or neither for the original function. And it can be neither. And in fact, one of these is neither. Let's think about it graphically. Let's try to draw the original function. Now, if you try to draw the original function, you're immediately probably feeling confused. Like, well, where does it start? And the answer is, it's up to you. Like, what point should I start at here when x is smallest? How high should I start? It's actually up to you because there's actually infinitely many f's that can work. They are all vertical translations of each other. They all have the same slopes at every value of x. So it actually doesn't matter exactly how high you start. I don't know, I'll start maybe here. When x is in this range of values here, f prime is positive. So the original f is increasing. And in fact, I didn't do a very good job there because this graph's increasing, the slope of the original f is increasing. I gotta draw a concave up graph actually. Until f reaches a local max is where there's an inflection point for f, and then it becomes concave down. It reaches a maximum evidently at this critical point because its derivative changes from positive to negative. So the slope of this graph changes from positive to negative. There's got to be a local maximum on that value of x. And the first derivative test would confirm that. It's changing sign from positive to negative. So f itself is changing from increasing to decreasing. Here the derivative becomes negative, so the slope is negative. It's most negative right about there. I got negative slopes that are most negative, say right about there. There would be an inflection point that's concave down here, then becomes concave up. The derivative is 0 right there. That's going to be a minimum. Because of f, the derivative is changing sign from negative to positive. That's what the first derivative test would tell us is happening with f. There's a minimum because its derivative is changing from negative to positive. Then it becomes positive derivative again. So positive slopes. Maximum positive slope right about there. So there's an inflection point. But then the slope goes to 0. It's 0 right here, but only for an instant, so to speak, before the slope becomes positive again. This critical point is neither a maximum nor a minimum. What happened with their first derivative test? Well, the derivative is not changing sign. It's 0 there, but it's not changing sign from positive to negative or vice versa. It's positive on either side of that value of x. the slope of the original function f is positive on either side of this value of x. So it's neither a high point nor a low point right there. So I'm visually thinking about the first derivative test here. In problem 40, the same figure is the graph of the second derivative. So we were looking at 38 here. Figure 4.14 is this one. In problem 40, they say that's the graph of the second derivative. Mark the x values that are inflection points of f. It's not where f prime equals 0. Inflection points of the original function the red graph is the original function, though I could translate it up or down. Inflection points of that are where the concavity changes. I've already identified them. Right there. A different color. Right there. Right here. Right here. And right here. Okay, okay. That is for the original problem. But we do have a new problem here. Sorry. So I'm going to redraw the same graph. But now it's supposed to be the graph of f double prime. Let's do this first, and then we'll go back to the previous problem and think about those inflection points that I drew. This is the graph of f double prime now. I'm not going to draw the graph of f. It'd be tricky. I'd have to draw the graph of f prime first, and then I'd have to draw the graph of f. But I'm going to think about what the definition of an inflection point is. It's a value of x where the sign of f double prime changes sign. Or f double prime changes sign, positive to negative or negative to positive. That's easy. These same spots, if this is the graph of f double prime, are inflection points of the graph of f. They're just testing, do you know what an inflection point is by definition? It's where f double prime changes sign. Oh, okay, so I made a mistake. It's only these two then. Not that one. Yes, that's where f double prime is 0, but f double prime is not changing sign there. So it's not really an inflection point of the original function f if this is the graph of f double prime. The concavity of the original graph of f is going to be concave up on either side. What will it look like there? Will it be concave up? Well, sort of, but I'm not going to get into details. So that's actually easy, but you want to focus on where f double prime changes sign. I do want to come back here to this situation again and emphasize why these are inflection points for the other problem. It was not part of the problem statement. But why are these inflection points of this function f based on this graph of f prime? Inflection points of f are the same places where f prime has local maxes and mins. Yeah, those same values of x here, 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 and here are the 4 spots where f has a little hilltop or a valley. F prime, I meant to say. F prime has a local maximum here, a local minimum here, a local maximum here, and a local minimum here. That corresponds to inflection points on the graph of f. Why? Hang with me, this is the last thing we do today. Why? I really explained it as I drew the graph of f. Over here, f prime is not only positive, but going up. So the slope of f is not only positive, but increasing. And concave up means the slope is increasing. To be a graph that looks like part of a smile, means the slope is getting bigger as you move to the right. That's what it means. In here, these values of x, f prime is decreasing. The slope of f is decreasing. It's positive, then becomes negative. That's what concave down means. That's why it's changing from concave up to concave down at this point. That's why that's an inflection point. Likewise, in here, f prime is increasing. So the slope of f is increasing. It's concave up. Over here, f prime is decreasing. So the slope of f is decreasing. It's concave down. And over here, f prime is increasing. So the slope of f is increasing. It's concave up. These are essential relationships that you want to work at understanding to see at an intuitive level, based on pictures, the relationships between these things. Yes, we have these formal theorems that we can prove that they are useful to really know something's true, but it's also good to know it at a gut level. And we do test you on that as well. Again, don't just walk out of here. Do your homework as quick as possible. If nothing else, when you do your homework problems, when you finish a problem, at least spend a minute thinking about whether it makes sense. Is what I did make sense? Maybe you find a mistake. Maybe it helps you understand what you did better. Does it make intuitive sense in terms of these ideas? Okay. All right. Have a good day.